Yeah, I have. Okay. So first, thanks a lot to organizers for inviting me. My special thanks to Nadia, who helped me today, and also to Sergey, who for very nice cooperation by emails. My talk is the title of my talk is on polynomial and regular maps of spheres. Okay, so let's make some. Okay, why I cannot? Okay, so I have problem to go to the next slide. Oh, okay. Okay, so this talk offers some result on intersection of algebraic topology and algebraic geometry. And I would like to say something what is inside of both sets. And the main result, which I'm going to comment, but I have no time for proofs, is the following theorem. If k is from 0 to 7, then elements of homotopy group pi n plus k of n sphere can be represented by regular maps from sphere of dimension n plus k to sphere Sn. To reach that, we fix first some background and recall necessary results as well.
Marek, may I ask you, regular map, you mean it is a smooth map without critical points, or is this something else?
I'm going to define this.
Yes, thank you.
Okay, so that is okay. So soon I'm going to present the finish. Okay, so this talk, all spaces are up to homotopy CW complexes, and we use standard terminology and notation from homotopy theory, mainly from the book of Wojtoda about homotopy theory. We don't distinguish between maps and its homotopy classes. We write iota x for identity maps of space, also for pointed space. We have the notation pi n x is homotopy group. You recall that starting from n, this group is Euclidean, and also there is a canonical action of pi 1 on higher homotopy groups. Excuse me, I moved too much. Okay, so let's make some introduction and answer Sergey's question. So now we start from some algebraic notion. Suppose we have any field, and X is subset of Cartesian power of this field. And we recall some notation from algebraic geometry, namely by X, we denote set of ideals of a polynomial ring of int and values. And it is well known that by Hilbert basis theorem, any ideal, if the ring of n variables with a coefficient k is finitely generated, then this X, which is the finite set of element of ideals, is coincides the set which is given by zeros of generators. But in particular, if k is reals, then this set of ideals is determined by unique polynomial, because there is special property of real numbers. Namely, the ideal, which determines any zeros of the interreal for reals, that is sum of squares. And the key examples in algebraic geometry, which are going to use, is the n-sphere. N-sphere over any field. Namely, if you have any field, then sphere over k, we define a set of points in k plus 1, such that the sum of squares is equal 1, and this is also algebraic set. This of the principal idea. Okay, and then we have some properties of the set which are going to analyze. Namely, if we assume that K is infinite and we have extension of this K denoted by L, then if you consider Zariski closure of sphere over sub KK, then we will obtain sphere from this extension. So in particular, we get that you have K, which is characteristic 0, then sphere over rationals is dense in the sphere over K. So we don't have this, this cannot happen in Euclidean topology, but we use here Zariski topology. And so furthermore, we have that if you take Zariski closure of sphere over rational numbers, then you take Zariski closure, then you have a real sphere. But also we have that if you take Zariski closure of sphere over rational, but we take this closure into bigger space now, then we can get sphere over complex numbers. I have here, okay, I escaped something. Oh no, now it's okay. Okay, so now I'm going to answer a Sergei question. So suppose that you have two algebraic sets, namely X and Y. X is included to M power of K, and Y is included to K power of K. A map between such algebraic set we call polynomial, respectively regular, if there are polynomial maps Pi, Qi, we are no polynomials, they are polynomials, such that this map is value of this map and the sphere is equal value of polynomial or quotient. So for me, regular map is polynomial or map given by rational functions. Also, we call polynomial map 4 of degree K if each coordinator is homogeneous map of degree K, as is determined by homogeneous polynomial of degree K. So we restrict only to polynomial or regular maps, or rational maps. And both types of maps we call regular. Okay, so now if you have algebraic set, then we use the classical notation that by J at X with the node set of polynomials which vanish on the X. And you have this ideal, then we define coordinate ring as a quotient of a ring of polynomial by this ideal J. If X is irreducible, then Jx is prime and Kx is integral domain, so we can consider field of quotients. Okay, now we have some remark. If you have two polynomial maps from X of algebraic set X and Y, then we see that if those maps are equal, if only if difference of coordinators belongs to this ideal J. In particular, if you have two maps of spheres over K, Sm and N, and both maps are polynomial, then are equal if only if difference of coordinators belongs to. So it's here. Okay, something is a mistake. Should be square bracket. But anyway, belongs to this coordinate ring. But we can show that this coordinate ring. Sorry, this coordinate ring. No, sorry, it should be here, not K by J. But we can show that this ideal is principal ideal if K is infinite. But it is true for any field. We don't assume that we have algebraic cross field. For spheres, we have special properties. Okay, and there is second remark. If you have two algebraic set, then there is bijection between polynomial maps from X to Y and K algebras of algebras of coordinated rings, but we have to change orientation. Maps from X to Y we replace on a homomorphism of K algebras, Ky to Kx. If K is actually closed field, then the only regular maps of algebraic set are polynomials. And that is consequence of Hilbert-Bluetooth theorem. And in the next slide, we are going to sketch argument of this. And the argument of the first is following. So suppose you have two algebraic set in field K, and then consider any map which is determined by a rational function. So we have such maps, then we of course we have assumed that Qi doesn't vanish at any point from X. So from this we have that you take intersection of X and set of zeros of Qi, there is empty set. But now we assume that K is algebraically closed. Then, but Hilbert Bluetooth null that and that, we have that associated ideal if a radical of this ideal from which it starts, so this from I plus a principal ideal determined by Qi, and that is the full ring of polynomials. This implies that one could be described as combination of Qi and some element from I. From this, it follows that you have the rational function on X. It could be replaced by Pi and alpha I. So, in other words, if you have a field of algebraic closed field, then any rational map on an algebraic set could be replaced by polynomial. So rational maps have sense if maps are if the field is not if it is not algebraic closed.
Mark, may I ask you once again? So the statement is that only a restriction to algebraic set, not in general. Polynomial map. Only restriction.
Only restriction. So let's summarize. We consider polynomial maps and rational maps, and those such two classes of maps we call regular. But if field is algebraic closed, then we can show using Hilbert-Bluetooth theorem that the restriction of this map to algebraic set always is polynomial. But over algebraic set. But we are going also to use some maps of spheres over reals, and in this case, it makes sense to consider rational maps as well. Okay, so the following question appears: which maps between spheres can be represented up to homotopy by polynomial maps or rational maps? From the differential geometry point of view, answer is all of them. So the problem exists and doesn't exist. And I'm going to sketch the proof of the first sentence. So I repeat it. From the point of view of differential geometry, any map could be represented up to homotopy by polynomial map. Why? Okay, so suppose that we start from some general fact, and from this we have answer. So suppose we have compact subset contained in the M Euclidean space, M power of R, and consider any continuous map from X to the sphere. The sphere could be included the complement of Rn plus 1. Thus, this F determines a map tilde from X to Rn minus 1 without point. Then we apply Stone-Weierstrass approximation theorem, and by this theorem, there exists a sequence which uniformly converges to F tilde. But Fk is, of course, sequence of polynomials. And also you can assume that coordinators of this pk are polynomials over rational numbers. And since this sequence pk uniformly converges to F tilde, we have that the value of this pk at x is non-zero, and F tilde at x is not equal to minus pk for all x from x if k is sufficiently big. Consequently, we get homotopy between F tilde and pk. And that is the proof of this fact. So, if in other words, if you consider another model of sphere, not algebraic, but a model of homotopical model, then you can show that any map between spheres, because this result is more general. So if we assume that X is compact, but now we can deduce that you have any map between spheres, and we consider it to replace sphere by its homotopical model, then any map has homotopy type of rational and of polynomial map, and polynomials are over rational numbers. Oh, so now let's record some history. A first result, it is Baum, from 1967, suggests wide affirmative answer. But later, on this question, Wood in 69 showed if n is a power of 2, then all polynomial maps from Sn to Sn minus 1 are constant. Consequently, the real polynomial representation is impossible in many cases. Among them, for example, the non-trivial element from pi4 to S3 cannot be represented by any polynomial map. And from this result of Wood, we have following corollary. If you have n greater to power of d, and suppose that k is 2 power d is greater than k, then any polynomial map from Sn to Sk is constant. Second, from this also we can deduce that if n is greater to k, then any polynomial map from Sn to Sk is constant. Okay, so here is a sketch of proof, but maybe I escape of this. So we from this result of Wood, we know that not all of maps could be of spheres could be represented by polynomial maps. But we have some examples when it could happen. So first, suppose if m is less n, then everybody knows that any map from Sm to Sn, in this case, is trivial. No, it's represented by constant polynomial. Second, if you have any map from Sm to Sn, and this map is not onto, then of course this map is homotopy trivial. And third is quite simple, but maybe it makes sense to also to mention this. If you have a self-map of cycles, then this map is homotopic to polynomial maps. And the same if you have self-map of S3 or S7. The point is that those spheres S1, S3, and 7, on those spheres there exists a multiplication. There is a problem with S7 because this S7 is not a group. No, but we only use power, and if you power, then we have no problem even for S7. And also there is some result which there is a formula, it's called Hopf formula, that how to creates polynomial maps. Namely, if you have a normal binary form, it means that if you consider norm of value, that is equal to product of norms of argument. So such binary map we call normed. And then if you have such form, then we can form quadratic form from sphere sk plus n to Sn, but there's the following formula. Value of this quadratic form on the pair is defined as follows. The first coordinator, you take difference of norms, x squared minus norm of y, and in the rest, we put 2 multiplied by f x and y, and you can show that using this property that the form is normal, that phi becomes polynomial map. So using this formula, now if you write for k complex quaternions and octonions, then and you consider multiplication of those two fields, then there's this whole formula. By this first formula, we can get very well-known maps called literature Hopf maps. So which denoted by eta, nu, and sigma. And so those three maps, by Hopf, are polynomial maps. And also we have explicit formula how they can define using this Hopf vibration. So let me say something about this S1, which was on the previous slide. So S1, as you know, it could be determined by set of complex number, not such that modulo is 1. And then if you take any map, then suppose that this map has Brauer degree n. Then this map could be represented by map which is defined by in such a way that value at z is n power of z. But then if you go to the real coordinator of z and you take a power, then z to n could be described as a sum of polynomial Pn plus IQn. And these polynomials which we got are real even polynomial over integers. And that is, and now if you follow the same procedure as for complex number, and now replace complex number by quaternions and octonions, also you can show that any map, self-map of sphere S3 and S7 could be represented up to homotopy by polynomial maps. So we have good example of polynomial maps, Hopf vibration and self-maps of spheres S1, S7, and S3. But what about others? Others we have result by Wood. If n is odd, then elements of infinity cyclic group pi n Sn corresponding to integer k, so because of this isomorphism, so an element for pi n Sn it could be associated with some integer k. And this element, according to Wood, could be represented by a form. Let me record that by form we mean polynomial maps such that all coordinators are homogeneous polynomial of degree, which is modulo of k. To state a result for even sphere, we define following object. If you have R between 0 and n-1, then we define such object. Sn sub R, it is set of sequences x0, xn, such that sum of sorry, here is misprint, should be x0 plus xr minus 1 to squares, and the sum to square plus square of s and should be equal 1. And this object is homeomorphic to a sphere. Then we have another result by Tourier, but is a long time later than Wood result. Namely, he showed that if you have any integer and suppose n is even, greater 2, then if k is odd, then there exists a homogeneous polynomial self-map of Sn with Brauer degree k and algebraic degree 2 absolute value of k minus 1. If k is even, then for each r such that to r minus 2 and n, there exists a polynomial map from this object which was defined before to Sn with a Brauer degree k. Therefore, for odd, it was very smooth what was show wood, but for even, as usual, these spheres are much more complicated, but the result that exists. Since real polynomial representing is impossible in many cases, it's still reasonable to consider complex representation, where many obstacles disappear and nothing happens up to homotopy. Namely, consider algebraic sphere over complex number. And definition is it's the same style as Fourier. So for sphere over complex, we define as follows: this set of sequences z0 to Sn from C from complex number of power n plus 1, such that sum square is equal 1. And this object we call sphere over complex numbers. And now observe that you have any point to this object, then using this relation, the sum square is equal 1, and we are going to, to real coordinates, we get the sum of squares of x is equal sum of square of y plus 1. And second property, we see that we have that x0 y0 plus xn yn is 0. So those two relations implies that complex sphere is diffeomorphic to tangent bundle of the sphere. No, but if you have this diffeomorphism, then this of course implies that complex sphere has homotopy type of real sphere. And we have another now a result by Wood, but it's from 1993. And Wood show if you have element of homotopy group pi n minus 1 and of sphere S to k minus 1, that this an element is represented by real homogeneous polynomial map of sphere. Okay, and but then its suspension is represented by complex polynomial map of complex spheres. If element of pi n Sn is represented by a real homogeneous polynomial map of sphere, then 2k-fold suspension is represented by complex polynomial map of spheres of dimension of complex spheres of dimension m plus 2k to sphere Sn plus 2k. Since we can realize every Brauer degree in odd dimension sphere, as Wood showed, by homogeneous polynomial maps, and the Hobbes maps are homogeneous polynomials, we have immediately corollary which as follows. Every element of homotopy group pi n Sn can be represented by complex polynomial self-map of Sn by very complex numbers. Second, elements of homotopy groups pi n plus 1, pi 2n plus 1 s to n, pi n plus 3 s to n, and pi n plus 7 Sn can be represented by complex polynomial maps of sphere of dimension which determined is by this homotopy group. But of course, for a complex sphere, we cannot discuss a regular representation because any map, any map determined by a rational function is represented by polynomial maps because of the algebraic closure of complex numbers. Okay, so now let's say something about regular maps of spheres, but over reals. So we recall some result by Bochniak and Kuchasz. And also there are some other authors, and the result is following. If you have a map of the real spheres from Sm to Sn, and this map is deformed, I mean it's the coordinates are determined by homogeneous polynomial, then if you take k-fold suspension of this map, then this k-fold suspension is homotopic to following regular map. No, it's a little complicated, but it means that, simply speaking, that the k-fold suspension is not anymore polynomial maps, but is represented by rational functions. From this, we get the following fact: element of homotopy group pi n plus k, if k is from 1 to 7, admit up to homotopy real regular representation. And that is the main result which I'm going to present this talk. No, but because of my time, I think I have 7 minutes. Is true? Is okay? Or I have to finish? Excuse me, do you listen?
Oh, no, you have
7 minutes.
minutes.
10 minutes, okay. Okay, so, but also we can show the following result. If you have weighted product of identity on the sphere, then this weighted product admit up to homotopy regular presentation. Regular, it means determined by, represented by rational functions. And this implies, using special property of weighted, that you consider now weighted product of identity and eta n, mu n, and sigma n. Let me recall that eta n is a suspension of Hopf version eta. Mu, it is also enforced suspension of the second Hopf vibration. Mu, and to say about sigma, it is suspension of the third Hopf vibration. And those three weighted products also admit regular presentation. Okay, but if you still have time, then also let me say a few words about generalization of this consideration. Namely, we can replace sphere by other object, and this object we are going to present now is Grassmann. So let K be real complex numbers or quaternions, then any Grassmannian could be described as follows. You consider all square matrices with coefficient in K, where K is R, C, or H, such that the A square is equal to A, and a conjugation of A is transposition. And the last property that the rank of A is equal to R. But if you have any bottom matrix, and mean that A squared is X, then the rank coincides with the trace. But so using this observation, we deduce that any Grassmannian can be described as real affine variety. For C, you cannot say that this variety over complex numbers, but over reals, it doesn't matter if you have R, C, or H, and the variety becomes variety over reals. And let IDM sub NR be set of all idempotent n square matrices with rank R. Then we can state the following fact. So suppose that K is CRCH, then there is a homeomorphism between tangent bundle to Grassmannian and idempotent matrices over K. So tangent bundle could be described by idempotent matrices. And there is a regular deformation matrix for idempotent to matrices to Grassmannian. No, of course, this deformation exists, but the fact is that this deformation could be described by regular map. Regular map means map determined by rational function. And the third property, there is an injection between set of homotopic classes from VC to V, but where V is subset of Rn and V sub C is the risky closure in Cn. Okay, so I think I'm going to finish. So wielkie spasibo za waszą uwagę. Thanks a lot for your kind attention.